Okay, welcome back. Once again, I'm Scott McDonald, and this is the second part of our discussion on acoustics. And today, or this part, we're going to focus on that other quantity we kind of alluded to in the first part, which is sound intensity. And then that will sort of bridge right into our last topic, which is sound source localization. Okay, so let's get started with sound intensity. So when we were talking about sound power, this objective number that we use for the inherent sound making capability of a device, we talked about a sound pressure method to get there. But there was also this sound intensity based version, and that's what we're going to start with today, or right now. And it's got its own ISO standards, it's got its own equipment that you use. And as we'll see, it can be more time consuming to perform. However, it can be used in situ, whereas the pressure-based one we described before is really only suitable for a semi-controlled environment. We talked about those correction factors, but those have limits to them, and there are certain environments that you can't really account for. That's where the intensity-based method really comes in handy. And as we'll see, there's more engineering inside. For our time investment, we're going to get some more information out, okay? So again, sound power is sort of the equivalent of our heater power in this analogy with our heater. And if we were to talk about the analogy for sound intensity, it would really be, let's study how the heat flows from one place to another. The heat comes out of the outlet of our heater more there than it does, say, the control panel or the bottom or something, right? The heat comes out more out of certain areas out of our heater, and sound is exactly the same. And so sound intensity is really concerned with the amount of energy per unit area, or watts per unit area, okay? And so we take the sound energy and we sort of map it to how much comes out given a unit area, and we measure it in such a way that we end up with a vector, okay? And so the intensity is the sound pressure multiplied by the particle velocity, okay? So if you break these units down, you have pressure, which is force per unit area, times a velocity, which is distance per unit time, get energy per area per time. That is the same as power per unit area, or watts per meter squared. And so we break down our object into a bunch of small areas, and then we say how much of the sound energy or wattage comes out in that square meter area, okay? And the sound's going to flow out of some places more than others, and we're going to map that out, okay? But if we map it all out, we can you can see how we get back to that original sound power value, as well as maybe some of that additional insight that we were talking about, okay? And certainly we have to be careful about how far away we are from the object when we're making these measurements, as intensity will be directly influenced by that distance from the source. So it's just something we need to keep track of, okay? So how do we do these intensity measurements? Well, we can't just use a standard microphone. We have to use a special piece of equipment called an intensity probe, which in reality is just a set of carefully matched microphones. So it's just two microphones instead of one. So if we compare these two tools, a single mic versus an intensity probe, the microphone measures sound pressure, right? And we can compare that to making a temperature measurement in our room with our heater. It has almost no directivity, so it doesn't really matter kind of how I'm holding it, depending on the style of microphone it is. And so as a result, we don't have a whole lot of an idea of where the sound we're picking up on this microphone comes from, right? I've got one sitting right here. We've just got this microphone, and the sound pressure waves could be coming from any direction. We don't really know necessarily where they're coming from. We just know what the pressure is right at the diaphragm of this mic, right? And so we're going to pick up the sound from all of the sound sources in our environment, so background noise, right? We compare that to an intensity probe. It's really two microphones now sort of placed face to face like this. And in doing that, we're going to measure not only two pressures, but we're going to have an idea based on the way these signals come in. If this guy gets the signal before this guy, then we know the sound's traveling that way. If this guy registers the pressure wave before this guy does, then we know the sound's traveling that way. Okay, and so by adding transducers to our measurement, we get some indication of the flow of the sound energy. Okay, and that's one of the big advantages of a sound intensity probe. This is also going to allow us to sort of back out or subtract the effects of these objects outside our measurement area, because we'll be able to subtract their effects because we know from which direction they're coming from. And by the way our measurement setup is performed, we're going to be able to subtract their effects much more effectively than we can with this pressure method. Okay. Now the fact that we have these two microphones separated by some distance, our delta R here in this graphic, this spacer distance is really going to control the frequency range over which we can measure with our intensity probe. Okay, and so we've talked a little bit about the wavelength of sound a couple times today, but lower frequencies have a longer wavelength. The physical size of the pressure wave in space, the lower in frequency we go, the longer that gets, and the higher in frequency we go, the shorter that wavelength gets. And as a result, we have some limitations on, for a given spacer distance, the lower and upper frequency range that we can measure. And so you see with a large 100 millimeter spacer, we can measure down to about 30 hertz, but only up to just over 1 kilohertz. Whereas if we put a 12 millimeter spacer in there, we can go down to 200, but almost, up to 10 kilohertz there, okay? And so the spacer distance will control the frequency range of our measurement. We can take multiple spacer distance measurements and sort of combine them in the software to get a full frequency band measurement for intensity. But wavelength plays a big part in that because we are using the phase match between these two signals to measure the intensity between them. Okay? So when we say the intensity probe can see where the sound is coming from, it's really a function of which signal comes in first, right? So if we call pressure 1 gets the signal first, and then pressure 2, or mic number 2, we can call that positive intensity, right? And we're measuring right along the axis of these two microphones. Whereas if it was going the opposite direction, we can give that a negative sign and call that negative sound flow, right? But again, we're measuring right along the axis of these microphones. If we have sound coming in 90 degrees to the axis of our microphones, the sound energy arrives at P1 and P2 at exactly the same time. So we, by definition, measure zero intensity. And so depending on whether I'm holding my microphone like this or like this, I might get the perfect answer or 0. So it's a orientation of our intensity probe is a big deal, because as we rotate it, you see we're measuring a component of the correct value. And so an intensity probe really only measures in one axis, and that's right along the axial direction of our two microphones for a face-to-face pressure probe. Okay, so really, really important to be very careful how we're holding our intensity probe, making sure we don't rotate it, over time or from measurement to measurement. We want to make sure that they're exactly the same if we can help it. Okay. So how do we get to sound power? Well, we're measuring the intensity. We know that it's watts per meter squared, right? So we end up having to surround our object under test in sort of this wire mesh. And this is sort of our test surface. This is how we're going to ensure that we test at a certain distance away from our sound source. And then we test over a certain area. This mesh creates our area. So then we take the sound intensity, or watts per meter squared, that we measure, multiply by this surface area, and that's how we get to our sound power. Okay, and so you'll see these meshes around a sound intensity test. Usually these are string or wire frames that you can use to help give you a visual guide for where you should be making your intensity measurements. okay? And as we do this, we actually have two options for the ISO standard. So you see this 9614-1 and ISO 9614-2. And the difference between these is one of them is known as the scanning method, and one of them is known as the point-by-point method. And the difference here is that they'll both allow you to get to the sound power by summing up your intensity and multiplying by the surface area. But the difference is this point-by-point method is going to give us a little bit more information. And let's take a look at an example and see how this works. Okay. So let's say we have our speaker here that we saw in our post-apocalyptic wasteland, and we're going to do some intensity measurements. And so we think, well, let's just do the scanning method because all I really care about is that sound power value, right? So we're going to scan continuously over our wire mesh test area. You see I've set up here this grid, and I'm going to use 9614-2, which is the scanning method, and I'm going to try to scan continuously over all of these grid squares, and I'm going to try to spend an equal amount of time at each sort of square in my grid so that I'm not biasing my average toward any one location on my speaker. Okay, so I take one measurement, 30 seconds long, and I scan over the whole thing. I get this intensity spectrum, so I see which frequencies carry more intensity, but I end up with a spectrum of intensity in watts per meter squared. I could then multiply that intensity overall level by my surface area, and I will calculate a sound power value. Okay, 104 dB in this case of A-weighted sound power value. Now, if I go the other route and I do the point-by-point method, which is 9614-1, I have my same sound source, my same measurement grid, but here instead of taking one measurement and scanning over the whole thing, I'm going to take all 30 seconds right here at grid A1. Let's say this cell is A1. Measure for 30 seconds. Then I go to B1 and I measure another 30 seconds. And then I go to cell C1 and I measure another 30 seconds. Okay. And so on and so forth until I've fulfilled all of my measurement grids. And you see I have 42 measurements. So I'm making a drastically increased amount of time spent measuring. 42 times as much time taking data. But the additional insight I'm going to get is that I can take these individual measurements and I know exactly where I was for every given measurement. And so I can not only calculate my sound power value from this by doing that summation and multiplication by surface area again, but I can also get to information like this, where I can now map out how much sound intensity comes from each one of these grid squares, right? And I can see, oh, for this sound source, more sound comes out of this area of my speaker than anywhere else. And so if this is a noise problem, I know just where to start working because this red area is responsible for more sound intensity than anywhere else on my speaker, okay? And so this is the additional insight that we get by spending more time taking our data. We can do this sound source localization. And this is how sound intensity bridges between our two topics today. This is intensity for not only sound power, but sound source localization. So sound power and sound intensity, what's the difference between these two things? Sound power, it's a single number for a given device and operating condition, and it gives you a certain number of watts of sound energy that it can make. Okay, it's a single number. We have a couple different ISO standards, either pressure array method or the sound intensity method. Both ISO standards will help you produce that single number. And it's great because it's objective and it's a standardized test. It's great for comparing measurements, comparing components between competitors and yourself, or maybe tracking your product development. Okay. Sound intensity, on the other hand, is a measured quantity, right? We're measuring it directly, but we need some special instrumentation. These two phase-matched microphones create an intensity probe, and we're measuring intensity directly then. And they measures for us the average sound flow per unit area, but it's a vector quantity, right? We now know the magnitude and direction of our sound flow because of this vector quantity. And it can be used to calculate sound power, but also bridge that gap to sound source localization and provide us some additional insight, okay? So that bridges us right into our second topic, which is sound source localization. So let's talk about this. So sound source localization, you're doing it all the time, whether you realize it or not. As a human being, we have two ears, right? And we can very easily tell, usually, where a sound is coming from. In front of us, behind us, left or right, up and down, because we have these multiple transducers. And we can tell along the horizontal plane, or what we call the median plane, where the sound is coming from, because our brain is very, very good at using these sort of specialized multiple transducers and then analyzing the way the signals come in to deduce where the sound came from. So how do we do this? Well, let's say we have this sound source off to our left here. There's something known as the interaural time difference, where the sound is going to hit, in this case, the left ear before it has time to go all the way around to reach the right ear in this case. And our brain can tell this very small difference in arrival time and tells us it's off to our left. And there's also the interaural intensity difference, where because this ear is closer and it's not shadowed, as we'd say, by the face at all, like the right ear is, we'll get an intensity or level difference between our ears. And so that helps our brain confirm, yeah, it's coming from over there, because we get both of these signals with both of these differences, okay? That's how our brain does it. Much the same way, all sound source localization tools are relying on multiple transducers to deduce where the sound comes from, okay? And we have two main strategies for this: intensity probes, where we have 2+ microphones, and then we have something called an acoustic array, where we have many, many microphones built into a single sort of device, okay? And both of these are have the ability to help us localize where sound came from, okay? So we have intensity-based tools and array-based tools. We're going to talk about both of these here. So going back to our intensity-based tools, we already know it is the study of the sound flow, like the heat flow from our heater. And this is really reliant, or helps us develop this vector quantity, where sound pressure and sound power are just scalar quantities. It's just a magnitude, right? We just know it's, in this case, 45.3 decibels. We don't know anything else about it. Whereas sound intensity says it's 46.1 that way. Okay, so that helps us a great deal to deduce where the sound is coming from, because we have this vector orientation as part of our intensity answer, okay? So this is a device called the Soundbrush, which is sort of a next generation sound intensity probe. So it's not just your typical face-to-face 2 microphone pressure probe. Those are sort of the classical example. The Soundbrush is sort of a next generation, and it allows us to generate plots like you see on the left here with the acoustic guitar. And so the Soundbrush is different because it doesn't force you to make this wire mesh and only measure at a certain area at a certain distance. We take care of all of that for you. And we do that, I've got one right here. We do that with a couple of the unique components here. So I'll zoom in on myself a little bit. So this is the Soundbrush, and you can see this doesn't look like 2 microphones face to face like you saw in those pictures of the intensity probe. You also see this sort of ping pong ball thing here. This plays a big part on it. But there are also some things hidden inside the handle here that are going to help us, and we're going to talk about each of these individually here. Let me get back to my overlay here. So first we're going to talk about this tetrahedral transducer. So if you can see, it's got 4 microphones in a tetrahedral configuration. And what's unique about this configuration is it allows us to, in real time, calculate the XYZ components of our sound intensity. So where our 2 microphone probe only measured in one direction, and if I was 90 degrees off, I would get 0, and this would be my actual answer. The sound brush doesn't have that same restriction. It's measuring in all 3 components of X, Y, and Z all the time based on these 4 pressure measurements we're making all at the same time. Okay, so that's one key aspect. The second key aspect is the internal gyroscope. So this is the component that I was talking about that's hidden inside the handle. And the gyroscopes in here essentially track how you're rotating this thing in space. So it doesn't matter how you hold this, the SoundBrush software is able to figure out, oh, he rotated it 52 degrees in the whatever plane, and it can compensate for that. So what you're seeing in this plot here, the red line is a standard traditional pressure probe in a fixed XY orientation, and then behind it are 49 different orientations of the SoundBrush held at all of these oblique angles, and essentially you see they are line for line the same. So we are 100% compensating for the rotation of this device in 3D space, essentially in real time. Okay, so that's the second key thing. The third key thing is this tracking camera and this ping pong ball. So what these do is this tracking camera essentially looks for this ping pong ball in 3D space and knows where you are as you're waving the sound brush around your object. So you're no longer restricted to having to measure a specific plane. You just go up to your sound source and wave this thing around. The tracking camera, the gyroscopes, and the tetrahedral configuration of the transducer essentially measure X, Y, and Z in real time without any restriction. And so when we took this data on this acoustic guitar, we essentially just scanned over the device and populated in a volumetric sense these sound intensity vectors. And so we get a very compelling 3-dimensional plot of how the sound emanates from this acoustic guitar. Okay, so let me show you real quickly in the software how this works. So this is the SoundBrush software. And the example I'm going to show you is actually not a 3D case, but you can see I just can test even a 2D plane. And so what we see here, if you can see it, is the dash, the front dash of an automobile. And part of what is really important in the interior noise level of an automobile is controlling how much sound gets through that front of dash, right? We might have an engine or a motor up there, and we want to keep the sound on the far side and out of the passenger cabin. And so to test this, we can put a broadband frequency source that's really loud in that front compartment and then measure the sound on the passenger side of that front of dash, right? And you could do this with an intensity probe, and you could, set up a grid and measure really carefully, the XY plane there and measure your sound intensity. But we did this really, really quickly with the SoundBrush, and I'll put these measurements in here. And I get this nice, compelling 3-dimensional vector information, so you can immediately see where the weak spots of this front of dash is. This is the steering column pass-through. So the steering column passes through, and there's a seal there. The seal had a leak in it this day, and we were able to deduce that very, very quickly just based on a total of about 2 minutes scanning with the SoundBrush. And I get these full 3-dimensional vectors showing me where the sound is getting through my front of dash. You see another possible weak spot over here, but all of this area is totally blue, low amplitude of intensities coming through there, so I don't need to worry about this over here. It's working great. I really want to focus my energy on these areas here. So I can not only get a 3-dimensional view of my sound intensity, but I can also do things like add a cutting plane here. So now what I'm doing is I have this cutting plane, and you can see this 2D sort of slice by slice view, as I move this plane through my three-dimensional set of vectors, I get the 2D result of my sound intensity shown right there on my same picture. So I can see, oh, yep, those are my two weak spots in my front of dash, right here and right here. And I can actually come over here and calculate a sound power value for those areas. So I have an area, I have the intensity. I can say these two areas are representing about 71.5 dBA of sound power. Okay, 71.5 for both. This guy alone is 70.5, so he is the majority of my sound power getting through. And so I can do some very, very compelling sound power analysis even from this 2-minute sound intensity test with my sound brush. Okay, so very, very compelling result in 3 dimensions. Sound brush, love it. Okay, so that's some intensity-based tools, both traditional and the sound brush. Now let's talk about the array-based tools we have. Okay, and these are all relying on the same sort of principle here. In all cases, we have some sort of antenna where we have a bunch of microphones, measurement being taken over here. And this is our sound source. And so the sound waves leave the sound source, hit our microphone array, and we do some back propagation or some processing to figure out where on our sound source the sound must have emanated from in order to arrive at our microphones in the way and order that it does. Okay. So there's this back propagation. We use a couple different algorithms for this calculation. Main topics or main techniques are known as beamforming and near-field acoustic holography. We're going to show you some examples of both of those today. And these arrays can come in any number of different kind of configurations. This is a device called the Sound Camera that Siemens has, and you can see it is configurable in size. And so just like the intensity probe and the spacer size determine the frequency range, same thing holds true for acoustic arrays. The bigger the array in terms of diameter, the lower in frequency it can measure because of that big span and the low wavelengths, or the long wavelengths at low frequency. One of the nice things that are very helpful about the Sound Camera is it can back propagate to a video. It's not just a static image. And so you can work on transient noises, things that are in motion, that sort of thing. And then for a diffuse field situation, like an interior of an automobile or an elevator or an aircraft or something, we have solid spherical arrays, which take the same idea, this technology, but put it into a spherical antenna and then can tell in 360 degrees where the sound is coming from. A planar array like this Sound Camera is really identifying sound that's in front of the array. Okay, and then all of these arrays can handle different algorithms, which is makes them all very, very powerful, from beamforming to focalization to near-field acoustic holography. And then you have specialized applications. You have large exterior pass-by antennas that we can use for exterior pass-by noise for automotive, or you can see we have really big applications for like wind tunnels for exterior wind noise. So specialized configurations are certainly available for an application like that. So the nice thing about the Sound Camera is it's truly point and shoot. And so you see this is a video of a wind seal test that's obviously on road in a vehicle. And we're assessing in real time where the leaks are in our automotive door seal here. So you can see there's obviously a problem here in the A pillar, maybe back here where the B pillar comes in. But it's even got a handheld grip here where we could just walk around our component and look at it in all different angles. And essentially this processing, what you're seeing in this video, is being done in real time. Okay, so it makes it a very powerful diagnostic tool where we can just sort of in real time do sound source localization. Okay. So let me show you some of the things we can do. So this is the sound camera software, and I've recorded a test I took previously. And you see a couple different displays here. This is the instantaneous frequency spectrum. You'll have an overall level versus time over here, and then this is the sort of real-time localization. So essentially this localization hologram down here is showing you where these frequencies that I have in between these double X cursors are coming from. So depending on what frequency range I select, I'll get a different answer. Okay, so if I move this around, you see the localization changes. Okay, one of the nice things about the sound camera is that I can do these motion or transient noises. And so in this case, we have a seat mechanism that had a noisy mechanism, and we want to figure out exactly where in the mechanism it is. So you can see the time history over here, and you can see these transient clicking events over here. And so I can just take this X cursors in my time domain, I can hit play, and essentially as I'm going through the time domain, I'm localizing these frequencies here, and I can tell where the noisy part of the mechanism is. Boom, right there. So you see that localization during these click events highlight the seat in motion in real time. Okay. And so there's no processing to do. There's no waiting to see what answer I need to get. It's all done right here in real time. Okay. So that is the sound camera. Now, to show you some of the other capability with this tool is we can also do take that data measured with the sound camera, we can bring it into TestLab and do some advanced processing with some more powerful algorithms. So we're beyond the point and shoot type of setup, and we want to move into, we have a more sophisticated problem. We need some more sophisticated troubleshooting. And so we will get into TestLab. Okay, so I take that same data from the sound camera and I can do some heavier hitting algorithm processing in TestLab. One of the things that we can do is called coherent noise processing. Okay, so in this instance, I'll zoom in on my picture here, but you see there are several people standing around in this picture, and these people are going to be my noise source. Okay, so imagine I've got multiple noise sources. Maybe this is an engine compartment, or you know, my air conditioner unit or whatever, but there's a bunch of things making noise in here, and I want to be able to tell which one is actually causing the issue. And because these are all human beings and they're all talking, the frequency content is going to be very, very similar between them. So I'm not going to just be able to say, oh, my compressor makes 4 kilohertz and my motor makes 2 kilohertz. So I'll just localize those two different frequencies and obviously be able to tell who's responsible. All of my sound sources in this example are making essentially the same frequency content, and so I can't just separate them by frequency. I have to do something a little more sophisticated. So here I've got my time domain, I've got my frequency domain here, and essentially just like in the sound camera, I specify a time and a frequency band, and I'll see the localization in this diagram here. So I say over all of this time, let's say these speech frequencies, compute and save, show me who my sources are. Okay, and so if I zoom in on this guy again, you see this guy, because he's closer, he's obviously louder, but this blue hologram back here tells me these guys are also making noise. I can't really tell which is my real problem here, because this guy just happens to be closer, so of course he's louder. But I suspect this might really be my issue. I want to be able to separate these two guys. Well, by adding an extra transducer or two, I can now intelligently process this data and sort of separate these two sources making the same sound or frequency sound. So you notice this guy's holding this cable. He's got a microphone. This guy's got another microphone. And so these are transducers I'm adding to my acoustic array. All right. So I measure with all my microphones in my array plus these two channels. And what I can do is I can see how much these guys are responsible for and how much this guy is responsible for by changing my averaging to something called coherence referencing. Okay, and so what I'm going to do is I now select one of these microphones. In this case, I'll select my second coherent microphone, and I'm going to basically tell the software only show me where sound is coming from that is coherent with this other microphone. Okay, so I say compute and save. Boom, this guy up front totally disappears essentially because I'm asking the array to show me where sound is coming from that's coherent with this extra transducer back here. So this guy's not correlated with that transducer like this sound source is. And so I can see 74.5 decibels of sound pressure is responsible from these guys back here. Okay, whereas if I go to coherent mic 1 and I show you that result, boom, I can see how much of the contribution he's responsible for, and this sound source disappears. Okay, so I can separate sound sources making the same exact frequency content and be able to separate them due to this coherent relationship. It makes it really helpful to identify, say, is our wind noise inside our car coming from, you know, the wiper or from the wind seal leak that I have in the A-pillar. I can separate those two by adding an additional microphone and providing it some sort of coherent relationship. Okay, so that's one application. Now I'm going to show you another application where we have multiple sound sources and they're all occurring at the same time, and we want to be able to get some idea who's responsible for what. Okay, so in this case, I'll show you what the picture is, and this is a room, and you've got a bunch of people sitting at these different tables. And if I turn up the volume here,
My voice sounds good. Jerry, my voice sounds good. Jerry, my voice sounds so good. I know he can get the job, but can he do the job?
so you hear a bunch of people talking all at the same time, and it's hard to understand what any of them are saying, right? Because they're all talking at the same time, all jumbled up, and the raw data isn't really that helpful. Well, using this tool, I can also do what we call virtual stethoscope mode, which is essentially, instead of saying, for this time and frequencies, show me on the picture where those frequencies are coming from, I can do reverse that process and essentially say, click on this picture and say, play me the sound that came from this area of the picture. So I've clicked on this guy's face, where the sound should be coming from, and you see it says back propagated. So now if I turn this up, see if you can tell what that guy is saying.
This pizza is the best pizza ever. I love this pizza. It's the best pizza ever.
I love this pizza. It's the best pizza ever. Let's try this guy back here.
I'll have a Coke, please. I'll have a Coke, please. I'll have a Coke, please.
I'll have a Coke, please. Sort of sing-songy, right? This guy back here.
My voice sounds so good. My voice sounds so good.
My voice sounds so good. So you see, I'm turn this down for just a second. You see the frequency information change when I click on different parts of the picture because subtly different frequency content comes from each place. Let's try this guy.
Jerry, I'm not arguing that with you. I know he can get the job, but can he do the job?
Okay. So if I play the raw data, it's all jumbled together. Whereas if I click on the picture, I can hear what comes from that area.
I'm not arguing that with you. I know he can get the job, but can he do the job?
Okay. So this could be, again, the inside of my air conditioner, and I want to know where is that squeak coming from. I could certainly hunt around until I find the squeak and I see the frequency content, and then I can confirm it using this method, okay? By saying, only play me the sound that came from this area of the picture, I can then hear what that signal sounds like, okay? One last thing I'll show you here is this near-field acoustic holography algorithm. And so what we've been looking at so far has been essentially beamforming where it's a certain type of algorithm approach. Near-field acoustic holography is a totally different mathematical approach for solving this sound source localization problem. And as the name suggested, it requires you to be in the near field. So we talked about the complex aspect of the near field in the first section today. Because we have so many microphones in that near field, we can sort of compensate for the fact that the environment's a little bit chaotic. We're capturing enough of the sound energy over all of our microphones to be able to make some sense of it. One of the benefits of this technique is if I show you what the localization in beamforming looks like for some low frequency. So I've selected 170 hertz to 550 hertz. And I'll just grab some time here. And so I'm just saying, show me where this low frequency energy comes from. And beamforming is kind of locked in terms of resolution to the wavelength of sound that you're using or that you're trying to localize. So you see I get this really sort of generic answer for this frequency range. If I make this even smaller and say, let's go from 170 to 230, and I say compute and save, it's kind of really generic, right? Because this frequency is so low that we're not really able to determine, is there one speaker on in this case? Is there two speakers? Is the speaker in the middle? It's just too generic, right? The wavelength of the sound we're trying to localize is too big to give us a specific answer. So what I can do is I can click this button over here, and this is going to force the software to apply near-field acoustic holography algorithm instead of beamforming. Near-field acoustic holography isn't so linked to the wavelength of sound like beamforming is, and so it's able to produce a much more specific example for low frequency. So if I say compute and save here, and for those same frequencies, I will get an answer. Boom. So you see the localization specificity. We call this spatial resolution. The spatial resolution for the INA algorithm, or near-field acoustic holography, is just dramatically improved compared to that of beamforming. So if I click back here on pressure and I say compute and save, you see I go from generic to very specific. Okay. And this is the power of the near-field acoustic holography algorithm. In addition, if you're really keenly aware of what's going on the screen here, you see that these units are watts per meter squared. And so the holography algorithm actually produces a back-propagated intensity where the beamforming does a back-propagated pressure. And so because I have intensity, I can also do some of that sound power calculation. I could tell you which of these speakers is responsible for contributing more of the sound power. So if I had an engine compartment or my air conditioner, and I've got my compressor and my motor and some other component in there, I could actually rank in terms of sound power the contribution from each of these multiple sources using this algorithm. Okay, so very, very powerful. Again, all of this data can be used in the sound camera software for sort of quick point and shoot. I can make a recording there, bring it over to Test Lab, and apply some of these advanced algorithms, okay? Which makes it a very powerful tool. So that is the end of our second part of our acoustics seminar. I'd like to thank you again for your attention. If you have any questions, thought of anything in the break, or heard about anything in the time in between you'd like to ask me about, my email is there. I invite you to email me. I'm happy to help out in any way I can with any questions or anything else. So thanks again.